Hello students. In this video we're going to talk about emission spectra, also called line spectra, and the Bohr model of the hydrogen atom. This was another early advance in quantum theory, and it's an example of how quantum theory was able to answer an experimentally observed result that the classical model of classical physics had not yet been able to explain. So in an earlier video I was talking about blackbody radiation, which is when you heat up an object and it glows. And a fundamental characteristic of the radiation that is given off by a blackbody object is that the electromagnetic radiation that is given off when it glows occurs in what's called a continuous spectrum. That is, all wavelengths are represented, sort of like the rainbow. The rainbow is a continuous spectrum of all visible wavelengths. However, we're now going to contrast that blackbody radiation with what happens when you pass electricity through a pure element. And scientists observed that when electricity is passed through a pure element, you can also get it to glow. It gives off radiation of a certain color. But that radiation is not a continuous spectrum. It doesn't have all wavelengths in it. The light instead that is given off when you pass electricity through a pure element is some combination of specific discrete wavelengths of light. So again, now we're not talking about the continuous spectrum of blackbody radiation. Now we're talking about emission spectra that occur when we pass electricity through a pure element. For example, hydrogen gas or neon gas. And as you know from neon lights, that when you pass electricity through neon gas, you can get it to glow. And the color that is given off, again, is in only specific wavelengths of light, not the continuous spectrum. Well, you may have seen the way that rainbows are formed by passing light through a prism, a glass prism, and how it will separate the different wavelengths of light so that you get different colors that are obvious within that light. So for example, the yellow light that comes off of the sun can be separated into a rainbow by a prism or a water droplet or water vapor in the air. And that's how we get rainbows. We can also use a prism to separate the specific discrete wavelengths of light that arise from an emission spectrum. And this will allow us to see the specific individual lines or wavelengths of light in that spectrum. And the resulting set of spectral lines is called a line spectrum. An emission spectrum or a line spectrum. And these line spectra are unique for every element. So the line spectrum for carbon is going to be different from the line spectrum of argon. So I'm going to just draw a little sketch here so that you can see what I'm talking about. I'm going to take a glass tube and I'm going to have electrodes, positive and negative electrodes, and I'm going to put electricity through it. And inside the glass tube, I'm going to have a sample of hydrogen gas, H2, right? Hydrogen gas is diatomic. It occurs as a molecule with two hydrogen atoms in the molecule. And when we zap this sample of hydrogen gas, it glows with some color. Okay? So I'm showing that some wavelengths of light are being given out. I can then pass this light through a prism. So we're looking at a triangular prism, a glass prism. And as the light from this glowing hydrogen gas is emitted from this discharge tube and passed through the prism, the different wavelengths of light are going to separate out from each other. Okay? And when they do that, they're going to shine on a detector, and the detector will detect a light band here a light band here, a light band here, and a light band here. And this is the line spectrum of hydrogen gas, H2. And it's a unique line spectrum. In the case of hydrogen gas, you get 4 visible lines, 4 visible wavelengths. And you don't see any lines or wavelengths in between them. So here again, this is what we mean by specific wavelengths only, and not a continuous spectrum that includes all of the wavelengths in here. So just to reiterate down here, scientists observe that when electricity is passed through hydrogen gas, the unique light that it gave off could be split into 4 visible spectral lines. And they occurred at these wavelengths: 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers. Now, if you recall that our visible light spectrum goes from about 400 nanometers, which is violet, up to 700 nanometers, which is red, we can see that this line is a violet line. That line is somewhere between violet and blue, so it's probably indigo color. That is in the blue region, so that's a blue line. And this is close to the red, so it's an orange color. So when the light was coming out of the glowing hydrogen was separated into its individual components, we found a violet, an indigo, a blue, and an orange line in the line spectra. Well, no one was able to exactly explain why you got these line spectra and why they were unique to every element, that every element would give its own set of visible wavelengths, and a different number of them as well. So how to explain this unique set of wavelengths? Classical physics was not able to do it until, in 1912, a researcher named Niels Bohr came up with a model, and it was based on quantum theory. So here is Niels Bohr's model of what he thought was going on in the atom that explained line spectra. So Niels Bohr said, I think what we have here now, based on the research that's just been done in the past 15 years from his time, from Rutherford and others, he knew that there was a nucleus in an atom, down in the center of an atom, and that's where the protons were. And he knew that electrons were outside the nucleus. And here was his breakthrough. He postulated that electrons existed at certain specific energy levels. And those energy levels for electrons were quantized. That is, there were not all possible values of 1.1, 2.3, and so forth, that those energy levels were somehow quantized, so that there were only certain possible values of energy, and you could not have energy values in between those. So, for example, let's say an electron was in an atom, like a hydrogen atom. You had one electron, right? Hydrogen has one proton, one electron in its neutral state. And even though you don't have an electron in them at any given moment, there are these other possible energy states or energy levels where that electron could be. So what Bohr said is he thought that when you passed electricity through this, the energy was absorbed by the electron, and it was excited or promoted up to a higher energy state. So this is a promotion or excitation. And that's what happens when you zap it with electricity. You put all this energy into it. Where does the energy go? It goes into increasing the energy level of the electron. And then what he said, he thought was happening, was that then this electron, now that it's in this excited state, having been promoted up from its ground state, then could possibly relax back down to a lower energy level. And it could relax back down to this level, or it could relax back down to this level, or it could relax all the way back down to its original ground state. And this was a relaxation, also called a cascade event, where the electron cascaded or relaxed down to a lower energy state. Well, the laws of thermodynamics tell us that we cannot create or destroy energy. It can only be transformed or converted into different forms. So when we put electricity into this hydrogen, we know how it was transformed. It was converted into the potential energy by moving the electron's position, its energy level. So it was converted to potential energy. And so this electron in the excited state had greater potential energy. Well, then when the electron relaxes or cascades down to a lower energy level, what is happening to the energy that it's losing? It can't be just destroyed. It has to go somewhere. And this was Bohr's great insight. He said when this electron then finally relaxes, it gives off energy as EM radiation. And the energy of that EM radiation, the energy of that light that is given off, is quantized. It depends only on the difference between this energy level and that energy level. So that energy gap. Or it depends on the difference between this energy level and that energy level. That energy gap. So we're looking at what's called the delta energy, the change in energy. So as the electron relaxes, it is undergoing a change in energy, and as it loses energy, as the atom overall loses that energy, it is emitted as light. And why are there only certain specific wavelengths of light that are given off? Because there are only certain specific energies that can be given off for that EM radiation. So do you see how this is an early example of quantum theory? Because it relies on the principle that energy levels are quantized. And by introducing this quantum theory element to this explanation, he was able to explain why only certain wavelengths or energies of light were given off in this process. It was an explanation that classical physics had not been able to achieve. So it was a major breakthrough. Well, let's fill in some gaps down here at the bottom. Electrons in an atom lie at certain ground state. Energy levels. That's what we call their energy level before they have been excited or promoted. Wherever they are when they started, whatever energy state that they were in, whatever energy level that they started in, we say that that was their ground state. They lie in those ground state energy levels until they are promoted or excited. So promoted to higher energy levels. How does this happen? Electrons are promoted or excited by absorbing energy, in this case, for example, from the electricity that we put into it. And that energy had to be equal to the amount of energy required to jump that gap. So this electron had to absorb an amount of energy in order to be excited. Electrons then relax back down to lower energy levels, and they could relax back down to any of the lower energy levels. And as they do so, they give off energy. They release or emit energy. And that energy that is released or given off is emitted as radiation, as electromagnetic radiation, as visible light. And finally, the energy of that radiation, the energy of those wavelengths that are given off, is equal to the difference in the energy of the two energy levels. So whatever this delta is, whatever this gap is right here, if that electron relaxes from there to there, it's going to give off exactly that much energy. It's not going to give off half that much or 2/3 that much. It's going to give off exactly that much. That energy is quantized. And that results in only certain wavelengths of light being given off. So that is the Bohr model of the atom, and it is another very important early application of quantum theory to explain physical phenomena that had not been able to be explained prior to this. This is 1912. Remember that Planck had just done his work with blackbody radiation and introduced the quantized energy levels in 1900. And then Einstein applied that to the photoelectric effect in 1905. So here, within a span of 12 years, is the introduction of 3 examples of a quantum theory that have helped take us from the classical model of physics to a new model of physics based on quantum theory, the idea that energy levels are quantized. So moving to the next page, I want to show you this chart. In the early study of the line spectra for the hydrogen, as I mentioned, only 4 specific spectral lines were seen. But after subsequent research was done, it was found that a lot more transitions were taking place in that hydrogen atom. It just so happened that only 4 of them occurred in the visible range of the spectrum. The 4 that were seen, because they happened to occur in the visible part of the spectrum, are these 4 right here. It just so happens that those energies correspond to wavelengths that fall into the visible range so that we could see them. However, there were many other transitions taking place, and with ultraviolet detectors, infrared detectors, and so forth, they could see that in fact all of these transitions were taking place. You'll notice that these transitions are all from a higher energy to a lower energy. You don't have to remember the names of these series. They were named after key researchers that helped elucidate them. But I have included them here because you might see those in your subsequent reading. Notice that these energy levels, n equals 1, n equals 2, n equals 3, all the way up. Theoretically, you could have an energy level of n equals infinity. But in a practical sense, we don't deal with elements with electrons in ground states higher than n equals 7. At least not yet. So, line spectra can now be explained in terms of quantum theory. To expand on that, there were a number of physicists that were doing research in this area. Balmer, Rydberg was a very important one. Bohr, as we mentioned before, was doing work in this area. And he was able to introduce his quantum theory, and he was able to come up with this relationship in which the energy of an electron at a given energy level could be calculated. So the E is the energy, and we know that's in joules, sub n, where n just means whatever energy level the electron is, and that must be a whole number because it's quantized. And it equals, that energy equals negative 2.18 times 10 to the negative 18 joules multiplied by 1 divided by the n value squared. So you're squaring the n value of that energy level. So you can actually calculate the energy of an electron if you know its energy level. Well, there's the equation, and here we have an example problem. Calculate the energy of an electron in the n equals 3 energy level. So go ahead and pause the video and do that math, and when you're done, resume, and I'll work it out for you. All right, returning to this problem, we have the Bohr equation. E sub n equals negative 2.18 times 10 to the negative 18 joules times 1 divided by the n value squared. Have to be very careful to make sure that we don't forget the 2 negative signs in there. And we don't want to forget to square that n value, okay? So here we go. The energy of an electron in the n equals 3 equals negative 2.18 times 10 to the negative 18 joules times 1 over the n value squared, so 1 over 3 squared. I could have easily converted that number into a number 9 in that denominator, but I wanted to make sure that you see that I'm plugging in the value 3 right there for the n value. Now if I do this math, and I should get a negative number out of all this, right? And it should be a fairly small number, and the answer that I get, rounded to 3 sig figs, because that is an exact number, is negative 2.42 times 10 to the negative 19. Units are in joules, as it should be because this is an energy. So there's my answer. The energy of a single electron, if it's in the n equals 3 energy level, has that value. So something I want to point out to you, this is a tiny, tiny, tiny amount of energy, right? We would expect that because it is a single electron. The other point that you may already have had questions about is this negative sign. How can an electron have a negative amount of energy? By standard convention, physicists and chemists have agreed that energy values for electrons will be given in negative values. And it's done that way because a lot of the other math that you end up doing on electrons works out neater if you treat this as a negative. And you can remember that because electrons are negatively charged, so they have negative energies. Now, in our next video, we're going to expand this equation to be able to calculate the difference in energy levels, the delta E, the change in energy, when an electron falls from one energy level to another. Obviously, if you can calculate the energy when it's here, and you can also calculate its energy when it's here, then the difference is just subtracting the value of one from the other, and you'll get the energy of that gap. And then once you do that, you can convert that energy, into a frequency and wavelength for the photon of light that is emitted when the electron relaxes.